I do what I want. All right, here we go. GCF. Yes, so this is going to be review of last semester. So those of you at home who don't have this packet, if you had Museo, you should be able to get this packet out. Those who had me, you're going to have to wait till the cohort tomorrow to get your packet.
You mean those who have Museo have to wait to get the packet?
No, she gave them the full packet. She was thinking ahead.
You gave us the full packet too.
Yeah, you be slacking a little bit.
I swear I have the full packet.
Feel free to look it up. Thank you, Snyder. Will somebody tell Benderman what's going on here? Okay. GCF. What does GCF stand for? Greatest common fact. What's going on here? Hey, Haley, put your mask on.
Oh, my bad.
OMG.
Gum in my mouth.
So what? That doesn't mean that we have to be infected. Greatest common factor. So what we're doing here is we're looking at both of these coefficients, then we're looking at the variables, and we're trying to factor out the most that we can have in common. So we start off 12 and 10, 2. Now this gets a little confusing, but think about, I have 3, so I took out a 2. That's what I'm making it. I'm making a list of all the stuff I can factor out. And then I'm going to build back what we had before. So I divided out a 2. Now I'm looking at the number of A's I have. This pile is 3 A's. This pile is 2 A's. So what's the most we can pick up from both piles? 2. We can only pick up 2. Thank you, Jacob. So I'm going to take out 2 A's. Now, that's what I factor out. Now here I'm going to look at what do I have to build back what I had before. So for instance, 2 times what would build 12? 6. A to the second times how many more A's would build 3 A's? So I need another A. Then I do the same thing again to build back the 10A squared. So I've got the 2. I need to build a 10. So what do I need? I need 2 A's. I've got 2 A's. So how many more A's do we need? None. This is what we call GCF factoring. This is the GCF. This is the greatest common factor. This is what you need to build back if you distribute. If I distribute this, I would get exactly what I had before. Now, we can do that again even when it's more complicated. So here, I'm going to start with the 14 and the 7 again. What does 14 and 7 have in common? 7. So I'm going to take out a 7. Then I look at the M's. What's the most number of M's that we could pull out? 2. There's 8 here, but there's only 2 here. So the most I could grab is 2. There's 5 N's. There's 2 N's. So the most I can grab is 2. Now, that's what I've factored out. That's the GCF. You guys take a second and try to build back what would have to be in the parentheses to build back what I had before. I'll give you about 20 seconds. You can check with a friend if you want to. Or you can sit there awkwardly quiet. Thank you, Benderman, for at least thank you for playing along. Look at Drew's way over here on an island all by herself. Ayla's on an island way back there. All right. Drew counts as, is it at an angle count? Does that count? Oh, man. And Drew's normally over here. This is so confusing. All right, let's see what it takes to build back what we had before. 7 times what makes 14? 2. Look, you already have 2 M's. We need 8. So how many more do we need? 6. I already have 2 N's. I need to build back 5 N's. So how many more? 3. Now this next one is a little bit tricky because people think things disappear and they don't. What happens is they just get divided out. So 7 times what number would make a negative 7? negative 1. I have 2 m's. I need 2 m's, so I don't need any more. I have 2 n's. I need 2 n's, so I don't need any more. This is what we call GCF factoring. And GCF factoring is what you should always, always, always check to try to do first. Because if you can GCF it, sometimes you can make your problem a little bit easier. Okay, the next move is what we call dopes. I think you guys will remember it when we see it, but you probably need a little reminder. And to start off, I want to first talk about the perfect squares. Who is the first perfect square? Huh? 2? 1? I hear a bunch of different answers. Why is it 1? The first perfect square is 1 times 1, which is 1. Who is the second perfect square? 4. The second perfect square, 2 times 2, is 4. Who is the third perfect square? 9, because third is 3 times 3 is 9. 4 squared is, let's see if you guys get through 12. 5 squared? 25. 6 squared? 7 squared? 8 squared? 9 squared? 10 squared? Now we get into the kind of tough ones. 11 squared? 121. 12 squared? And how long does this list go? It can go as long as you want it to, right? So there is a 1,000,000th perfect square. There's a 1,256th perfect square. Perfect square. Okay, so what's the rule when it comes to breaking down? I call this dopes. Difference of perfect squares. So this only works. She just calls it difference of squares. I call it difference of perfect squares. Same diff. This only works if this term is a perfect square, this term is a perfect square, and there's a minus in the middle. You remember difference means subtract? There's no such thing as SOAPs. Well, there is, but it involves imaginary. There is no sum of perfect squares. Okay, so this is how it works. A squared minus B squared. Now look, as a reminder, every factoring problem should have parentheses. When you're done factoring, you should have parentheses. Now, when it's dopes, does anybody remember what happens to the signs? One is a positive and one negative. Now, you don't have to put the positive one first. You can put the negative one first. That's fine. Now, the rest of this, just think about what makes sense. What times what would make A squared? A. So this is an A, and this is another A. What times what would make B squared? B and B. And now look what happens when I distribute this. I'm going to do this on the side. You don't have to write it down. If you want to, you can, of course. But I just want to show you that this thing does work the way that we think it should. I'm going to distribute this. What's A times A? A squared. What's A times negative B? Negative AB. Now this is where it gets interesting. What is B times A? Positive, and you could call it BA, but I'm going to write it in alphabetical order. BA and AB are the same thing. And then look what happens at the end. A positive times a negative is a B times B is a B squared. But look what happens right in the middle. They cancel. Subtract AB plus AB adds up to 0, and we're left with A squared, minus B squared, just to show you that it works. So how do we recognize it? Well, you first have to recognize that you have perfect squares. What's special about the numbers 9 and 49? They're odd. Yeah, that's true. But what's special about them besides that? What's more special about them? They're perfect squares. I know the answer to a factoring problem has parentheses. These are perfect squares, which means it's a dopes. So I know another thing. What else do I know? One of them's a plus and one of them's a minus. Then from there, I think about what does it take to build these pieces that I want. Now, if I want to build a 9, I could do 9 and 1, but we're supposed to be squaring stuff. So what numbers should I use instead of 9 and 1? 3 and 3. I need 2 x's, so I should put 1 x here, and I should put another x there. What do you think? You do the second half. I'll give you 10 seconds. 9, 8, just the second half. What goes in these blanks? 6, 5, 4, 3, 2, 1. What times what makes 49? What times what makes y squared? Bum, 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 bum. What do you think? Easy peasy? Look at number 4. What's special, what isn't special, I should say, about 72 or 2? They're not perfect squares. So what do? This is in the dope section, so it must be a perfect square problem. Yes. Don't forget, you're always supposed to look for a GCF. So when I look at 72 and I look at 2, is there anything they have in common? I'm going to take out a 2. Why did I take out a letter this time? Good. They were very excitedly answering that the other term didn't have a C. Now you got to build back what you had before. So I got to build back a 72. 2 times what is a 72? 36. How many C's do I have out front? None. How many do I have out front? None. How many do I need? So I got to give all 4 of them inside. Does that make sense? My bad. On the first term is what you... Okay, I took out a -2. I had a -2. I divided out a 2. What should be left behind? -1. Now, if this was Algebra 1, I'd be jumping for joy if you could get to this spot, and we'd call it. But this is Algebra 2, and then leading into pre-calc next year. We have to keep going if we can. What's special about the number 36? It's a perfect square. What's special about the number 1? It's a perfect square. What's special about c to the 4th? It's a perfect square. Who is c to the 4th a perfect square of? C squared, c to the 2nd. Okay, so I'm going to break this down again. I know my answer is going to look like this because all factoring answers look like this. Where'd this 2 come? Well, that's because we factored the 2 out from the beginning. 36 is a perfect square. 1 is a perfect square. They're getting subtracted, so that's dopes. I know 1 is a plus and 1 is a minus. You finish it. You finish it. Let's see if you can do the next part. 10 seconds. All right, let's see how you did. What times what is 36? What times what is c to the 4th? Oh, man, you guys are good. C squared. So there's 6 times 6 makes the 36. 2 c's and another 2 c's make 4 c's. What's at the end? 4 c's? Sound like I said horsies. Little horsies. Little horsies. Okay, you guys do number 6 next. Let's see if you can do number 6 before we go on to number 7. I'm going to take a lap around. This is your chance to ask for some help if you're here. If you're not, you can ask something in the chat. Yes. So what you're taking out is what goes into both of those. So what goes into 7 and 28? 7. 7. That's why you took out a 7. Now you move on to the m's. What's the most number of m's you can take out? Well, how many m's are here? How many are here? Whoa, how many are here? 1, right? So if I had a pile of 7 things, and I had a pile of 1 thing, and I have to pick the same amount from both piles, what's the most I can pick up? Here's 7, I don't know, 7 pennies. Here's 1 penny. When I reach into the piles, I have to bring up the same amount. Well, could I bring up 3? Could I bring up 3 pennies from a pile of 1 penny? No, what's the most I could bring up? 1. Now that's gotta be m to the 1 though. Those were m's that we're talking about. Now, how many n's do we have in common? What's the most number of n's we can pick up? There you go. Now give me a parenthesis. That's all the stuff that you have in common. Now you go and you build back. So what would that need? 7 times what makes 7? Oh, 7 times 7 makes 7. 7 times 1, which you can either not write or write. How many m's do you need? Right, because you have 1. How many more do you need? And then how many n's? We have 1. How many do we need? Wait, how many do we need here? That's n to the what? Whoa, answer me first. N to the what? 1. How many do we have? So do we need another one? If we put this back in, you see how that would, does that make sense? We don't need more n. Now, I'm gonna actually do this one, and then we're gonna come back to this one, so don't get confused if I'm talking about number 6 next. All right, let's see how we did. 10 and 10 are both divisible by 10. Good. W to the 5th and W are both divisible by W. That's what we call the GCF. That's what we've factored out. Now I try to build back what I had before. So 10W to the 5th, 10W to the 1st. So 10 times what? 1. How many more W's do I need? 4. 10 times what makes negative 10? Negative 1. How many W's do I need? No new ones. I don't need any more. What's special about W to the 4th? It's a perfect square. What's special about 1? It's a perfect square. So I can factor this again into W squared plus 1, W squared minus 1. So once you GCF factor, sometimes you have to go again and you have to factor it down again. Okay, let's go back and let's do number 5 together just because the m's and the n's could be a little bit confusing. What does 7 and 28 have in common? 7. How many m's do we have in common? We have 1. There's 7 m's here. There's 1 there, which means I can take out 1. How many n's do we have in common? There's 1 here. There's 3 there, so the smaller amount is 1. Okay, now that's all the stuff that we have in common. Now we have to build back what we had before. So 7 times what would make 7? 1, so I don't care about it. I have 1 m out front, but I need 7, so I need 6 more m's. I have 1 n. I need 1 n, so how many more do I need? 0. Now we move on to the second piece. 7 times what is negative 28? How many m's do I have? How many do I need? So I don't need any more. I don't want to give any more to that piece. How many n's do I have? How many do I need? So that means I need 2 more. What do you think? In Algebra 1, we would stop there. This is Algebra 2. So I would expect you to recognize that these are perfect squares. I know they don't feel like it, but they are. Let me show you what this breaks down into. That's still out front. One's a plus, one's a minus. Let's actually do the second part first. What would make 4n squared? I need a 2 and an n, a 2 and an n. What times what would make m to the 6? Think about it. How many n's were here? 2. So how many did you break down here? 1 and 1, because 1 and 1 makes 2.
Would it be 3?
It'd be 3 m cubed and m cubed. Yes. The comment was, when you multiply, you add the exponents. That's what we did at the beginning of this unit, and that's exactly why we got 3 and 3. Now that's pretty high level. I would not put, maybe I would put it on a test. Maybe. Probably not though. Okay, I'm going to skip these two. We're going to come back to them either tomorrow or if we have more time in this hour. And I want to talk about a grouping, a move that I call factor by parts. I don't know. I was going to say something different, and then I had to say I don't know again. You might have done this in Algebra 1, but didn't you guys not get all the way through Algebra 1 or something like that? Yeah, that's because of COVID. Do you remember factoring, using the slide rule factoring in Algebra 1?
Yeah.
Okay. What's that? Oh, what? Snyder. Oh my gosh, Snyder. I'm glad you do some work in my class. I appreciate it. Okay. When do we do factoring by parts? The dead giveaway is when you have 4 terms. This is the only move we have in our arsenal of factoring when it comes to 4 terms. It's the only way we can do it. So what I'm going to do is I'm going to make this into 2 parts. That's why it's called factoring by parts. I'm going to make this a part, and then I'm going to leave this open, and I'm going to make this a part. There's a reason I leave that open in the middle, is because that sign has to come down into the next level. Okay, so once we've divided it into 2 parts, we are now going to factor each one of these with GCF factoring. So x to the third and x to the second, what's the most I can factor out? I can take out an x to the second. I'm just factoring these 2. If I took out 2 x's out of this, what does that leave behind? X. If I took 2 x's out of this, what does it leave behind? 1. Not 0, not nothing, but 1. Does that make sense? If you don't believe me, distribute. Just distribute. You should always be able to distribute and get what you had before. X squared times x is x cubed. X squared times 1 is x squared. We got what we had before. Now this is the part that's kind of tricky. No matter what, that middle sign has to come out. Sometimes it's a plus, sometimes it's a minus, but that term must come out. Now, I don't care what the signs are of these two. I just care what the numbers are. Does anything go into 4 and 4? 4. Okay, now, step back. What is your GCF in this piece? -4. Why is it -4? Because of the sign. You see what I'm saying? So once you factor out, you really got to think twice about that number out front. So let's go back up here. We divided out a -4 out of -4x. So what's left behind? X. +1. We had a -4 and we took out a -4. We had a -4. We divided out a -4. So that left behind a +1. So this is the first check to see if you're doing this right. What do you notice about the parentheses? They're the same thing. So what happens is these two come together to make one of your answers. And I like to cross them out because then they kind of cross out. And what you're left with is your other answer. That's your 2 factoring answers.
Oh,
What do you think?
that's kind of weird.
Now, if you don't believe me, I'm going to do a quick distribution to show you that this does work. Watch. What's x times x squared? X to the third. What's x times -4? What's 1 times x squared? What's 1 times -4? Now, this isn't in standard form, but are all the same pieces. X cubed, x cubed. X squared, x squared. -4x, -4x. -4, -4. It's the same thing.
Oh my God.
Now, why are we still, though, not done with this? What's special about this? This is a perfect square. So we would actually go one more time and make this x plus 2. My bad. X plus 1. My bad. X plus 2, x minus 2. Then we are done.
Will they always end up having to have the
No,
Okay. We just have to look out to make sure.
correct. You guys try number 21. Or should we do one more together?
No, let's just do it.
Does anyone want me to do one more together online? We'll come back to this. We'll do this again in a second. Or I'll do the answer for you, but. You have a question? What did that thing do? So divide it up here. Now look at the first section. GCF, the first section. What do they have in common? How many x's?
Isn't one technically the same for this one?
Whoa. We're looking at this group
Yeah.
and then separately this group. So just look at this. That's why it's called factoring by parts. We just look at this part first. So in these two, what's the GCF? What's the most you could factor out? Good. So then out front,
So then it would be
then parentheses, and builds back what we had before. Whoa, we're still in this section. This is all just this part.
I think my locator remembers it. And now that I've seen it.
I remember it too, but I just can't.
I want you to just use these two. So when you took out two of these x's, what would you left behind?
Oh, sometimes it's.
Now you took out, yep, and then you took out two of these, what would you left behind if you took out the x squared? Close. Yes. What kind of one? Close. Now that's all the first section. Then you take this sign, that goes in the middle. Okay, now you're looking at these two. What do these two have in common?
And so it's like this, which I've never. So your father was spider charging.
Good, so what we
And I
factor
was
out
reading the
front?
dictionary.
Whoa, is that the biggest number that goes in the 99?
You're like in the middle, but closer to like the north or like.
What's the biggest number that
Oh,
goes in the
I
99?
said, like, no, I drew. Like, but I wrote down, if we just look straight, right
Okay,
there.
now parentheses, tell me what would be left behind if you divide out the 9.
But it's also like,
I think he's actually
what do you mean?
that's close to it.
Okay, so you don't know. Look, I'll show you what it looks
So
like.
now tell me where you
I
got
don't know
this
who
3
he
from.
said.
Here's my picture. I don't know. And then I drew a photo of no, it's behind.
Yeah, but the question was, you took out the
Like, he
9.
has no photo,
So you have to say 9
Yeah,
times
like he's
what?
not a specific.
Makes
No.
9.
Like, this was a picture that I was like, doing homework.
Who'd leave behind the what?
And I just gave him.
Yeah, that would make sense. But the problem is, this number out here is what you divided these by.
I think
So if you took 9 and divided it by 9, what would be left behind?
And then there was like dark pen lines.
Which one?
Like definition.
Watch why this doesn't work the way you got it. What's 9 times 3?
So what did you come?
No. What's 9 times 3? Is that what we have here? If you distributed, what's x to the 2 times x to the 1? X to the 3. Good. What's x to the 2 times negative? That's negative x
I
to
wrote
the
the
2.
word down.
But you gotta do the same thing here. 9 times what is negative 9? 1. And you don't even have to write it if you don't
You're
want
like,
to.
it's a mind game.
What's 9 times 1 x?
I'm not gonna.
No, let's check it. What's 9 times 1 x? 9 what? What's 9 times negative 1? See how it builds back? That's how you check. Let's go up here. What's x squared times x?
Yeah, I think I did.
Boom. What's x squared times
Okay,
1?
but then second semester, I.
Boom. What's negative 4 times x? Boom. What's negative 4 times 1? You see how it builds back? You should be able to do that to build back. Now, from here,
I know.
You only need to go like this. One of these, if they're the same thing, that becomes your first group. So what would your first group be? You have the things that the same. What's in this parenthesis? Yeah, they should look kind of weird, but they are the same thing. Now cross those out, and what's left over goes in the other one. You're welcome. All right, gang, let's try it out. Factor by parts. Here's one group. Here's another group. And I always leave that middle part open. Okay, x squared and x cubed have an x squared in common. That leaves behind an x and a minus 1. So what I've done is I've taken two x's out of each one of these. 9 and negative 9 have what in common? 9. Now I don't have a choice. It has to be plus because that's what's in the middle. 9. Now I divided out a 9 out of 9x. What's left behind? X. And then negative 9 divided by 9 is negative 1. Now I know what my answer is supposed to be. My answer to every factoring problem is supposed to look like that. So how do we get from this line to this line? Well, it turns out these come together and make one of your factors. What's left over makes your other factor. Now here's the question from before. Is this a perfect square again? Yeah. Is this a perfect square? Yes. Is that a perfect square? Yes. Is this a difference? No. If I factored this, let's say that you tried to factor this, and you did x plus 3 and x minus 3, look at why this won't work this time. What's x times x? X times x makes x squared. Then I would have a negative 3x and a positive 3x, which would cancel. That's good. But what's 3 times negative 3? Negative 9. This does not work this time. This is what we call SOAPs. Sum of perfect squares. And if you want to try to factor a SOAPs would look like this. X minus 1, x plus 3i, and x minus 3i. That's how that would factor. Because remember, when you do your I times I, you get I squared. And what did we do with I squared? Cross it out and switch the sign, turns it back into a positive. If you don't remember that, I'm not getting into it right now. Let's have you try 22. How about people at home? How you doing? Anybody have questions? Silence. Okay, let's go. 22. 22.
I have a question.
Yes.
Is this like, I think this is right, as simplified as it can get.
Almost. You've got to take something out of this. What's a number that always goes into everything?
1.
1. So you want to put a 1 there.
Oh.
No, not there. No. Out
Oh,
front.
man.
Then you factor it out. Just like you took out that k squared, you have to take out a 1 every single time. And now, are your groups the same?
Oh, it's a negative. Oh.
Yeah.
And so now you can go into your parentheses from here.
So I have to go into.
That's one of them. What do you think?
Squared minus 1, and then that's it.
You're good. Because you took out a negative. So what would be left out of negative k? You took out the negative. Good. And then the negative 5, you take out the negative. Are your two groups the same? That's the key. What's up, friend? Okay.
I thought that should be.
Well, then you have to do it again.
So these two, right? What's the most? Oh, I think you got it. Oh,
I ran
they're
it
all
too.
kids. So you
I
wanna
just kept
do them
going.
in order.
It's no. So.
Yeah, so I don't have.
So I wanna take these in groups of the first two and the second two. And I wanna leave this one. So what goes into both of those? Parentheses. What's left behind? Close it. Now, take out the negative no matter what. Now, this is weird, because it doesn't feel like anything goes into them, but what number goes into every number? So then take out a 1. Parentheses, you take out the negative, what would be left? Good, positive what?
you need to get a fifth at least. To get
If you
it
got
done.
the negative, what would be left?
No,
Which one?
I put them in there.
If I divide out the negative
Because
one.
I'm pretty sure you need at least a G. I mean, it barely touches it, so I'm like, I'll take this with mine until you want it.
And this.
I'm pretty sure you need at least a G, you need to get one time, I just touched it. To get it.
So then what are you gonna write this parenthesis?
Dude, a farm? And now you're
Right
giving
there.
me
The piece that's the
But
same
they
is
have
in the
to prove
first
that you're qualified
parenthesis.
to do something.
Then you can kind
But
of
you can,
cross them
well,
out.
it's nice that you're not.
What's left behind
And
is
I'm
the
almost
other
positive
two.
you need it. You either need to be completed, or you need it completed.
How do you
Okay,
know?
okay, well, you need to care.
But it.
How are you gonna move to Colorado if you can't get a job and save up money?
Train,
All right, let's see how we did. Group,
Hello.
group. All right, so here's my groups.
That's what I thought he said.
K cubed, 5k squared. What do they have in common? K squared. That leaves behind, I took out 2 of these k's, so that left behind 1k. I took out 2 of these k's, so that left behind the 5. I don't have a choice. The minus sign has to come out. Now, when you look at 2 terms that don't feel like they have anything in common, you have to use the number that everybody has in common, which is 1. Now, I divided out a negative 1 out of negative k, so that left behind a k. I divided a negative 1 out of negative 5, so that leaves behind a 5. Why is my math voice happy? Why is my math voice happy when I see this? Because the parentheses are matching, which means I know that my next level, my answer to a factoring problem, should always be parentheses. One of my parentheses is the piece they have in common. What's left over goes in my other parenthesis. If I box this in, I would get 2 out of 3 points. Why wouldn't we get full credit? Because it's a dopes. This is not a dopes. That's a 5. It's not a perfect square. This is a dopes. So I would break this down again. One's a plus, one's a minus. K times k makes k squared. 1 times 1 makes 1. Now I box it in and put it up on my fridge. Well, the neighbor lady comes over to borrow some milk or something. I want her to see it because I'm really proud of my work. What? Oh, no, she'll see it. Trust me, people don't recognize math. Okay, you guys try number 23. 23, get to work. Make the trace.
Oh.
Sometimes I forget that I can do that. What goes in the form 5? How many V's is the most we can take out? Oh, 2. So now you make parentheses. You took out 2 of the V's. From 4 V's, you go up to that. Well, how many? 1 V. Good. You took out 2 V's out of negative 5V squared. What would be left behind? Good job. Here's your first one. Now, you don't have a choice. That has to come up next. 16 and 20, what do they have in common? Okay, now from here, you're taking out a negative and a 4 out of the negative 16b. So what would be left behind? Sure. Then you're taking a negative 4 out of this 20. Close. If you divide 20 by negative 4, what would it be? Now, why is your math always happy? Same thing. Go get it. Go. Oh, so close. You're gonna be laughing when you get it. Hey, we don't laugh at each other. Mockingly. Snyder. How we doing?
No, listen, you're not good at lying, your whole face is red. You can't lie to me.
She's going ham.
How do we know that we're gonna factor by parts?
Because there's
Because there's 4 terms. And anytime you see 4 terms, that's a factor by parts automatically. Group, space, group. 4 and 5 have what in common? 1, so I don't want to write it. V cubed and V squared have what in common? V squared. So that leaves behind, I took out only the 2 V's. So that left the 4, and it left one of the V's. I took out 2 V's, that still leaves the -5. I don't have a choice, I've got to have the negative. Now I look at the 16 and the 20, what do they have in common? 4. So what did I actually factor out of this second group? A -4. So when I build back, this has to be a positive 4V. What's 20 divided by -4 would be -5. Why is my math voice happy? Because the groups are the same. So I know my answer to every factoring problem looks like this. When it's factor by parts, this becomes one of my answers. What's left over becomes my other answer. Box it in and put it up on your fridge? No. Why not? Because we got dopes. 4V minus 5. This is going to factor into plus and minus. Sadie, what times what makes 4? Wait, what? What happened? All right, 24. Let's go. We're getting so good at this.
Amazing. Guys, is visitor parking is that over there?
I don't know. Will you get to number 23?
4.
24.
Wow. Good job.
Wow, bro. Actually, I'm not going to wait for you on this one.
How come?
Oh, he thinks it's my real voice.
I'm not even going to talk. I'm just going to show the word.
That's fine.
Alright.
Bro.
For my community. No, they're like my age.
The only thing I have my age
I live in Grand Haven, so.
So can we break this down again? 9's a perfect square,
Down is
and it's subtract. Why can't we go again? It's not x squared. So this would be the end of it. We can't break this down because what about 2 and 7? They're not perfect squares, and it's not dopes anyways. It's soaps, right? It's a plus, so we couldn't even do it anyway. This is the best we could get. Okay, I want to go back up and review. I know we won't have long. We're going to maybe just do, I think we'll just do one more example, but I want to review with you how to do the slide rule again.
Come on now, we know how to do that.
Not everybody does. Okay, so first of all, how do you recognize dopes? Perfect squares and how many terms? 2, 2, 2. They have to have some perfect squares in there as well. How do you recognize factor by parts? 4 terms. How do you recognize slide rule? That's fine. No, is 3 terms. Okay, so I'm going to make up a problem. Yep. I got to remember. Let me make up a problem. Yep.
This is so extra.
Yeah, this one takes like forever to do like 2
Oh my God.
This is
Please keep whining. It really is helpful for me. I really enjoy.
You're gonna say
It
it doesn't take forever.
doesn't take forever.
It does.
It doesn't take forever, but it takes a long time.
Because you guys aren't very good at it yet. Okay.
Are we doing that problem?
Yes.
Oh.
So we're going to do this together. So those of us who have forgotten the slide rule, this is your chance to remember it again. And those who have never known the slide rule, this is your chance to learn it. Of course, we'll do many examples that'll give you more practice. But this is where we are right now. So the first thing I'm going to do is I'm going to make this x. And I have to fill in all 4 sections of this x. I start by filling in the top. And the way we find the top is I take the first number and I multiply it by the last. Mult. 2 times negative 12 is negative 24. Then whatever number's in the middle, that goes on the bottom. Now I'm going to try to find 2 other numbers on the sides that have to multiply. So that's a little multiply dot there. They have to multiply to make negative 24, and they have to add to make negative 5. Some people are really good at just looking at it and figuring it out. If you can't figure it out, make a list of all the numbers that go into negative 24. So let's make this organized. I'm going to start with 1. Does 1 go into 24? How many times? Does 2? How many times? Does 3? How many times? 8. Does 4? How many times? Does 5? No. So the next number that would work would be 6, and we've already got it, which means if you go in order, there's never any numbers that'll work. If you go in order. If you jump around, that's not going to work. Okay, do any of these add or subtract to make a 5?
Yes.
What ones? 8 and 3.
-8.
Now, what kind of 8 would I need? What kind of 3 would I need to have them add together to make a negative 5? A negative 8 and a positive 3. So let's just double check that. So negative 8, come on. Negative 8 times 3, there's my negative 24. Negative 8 plus 3, that adds up to be my negative 5. What do we know is the answer to every factoring problem? What does it look like? 2 parentheses. So now I'm going to go parenthesis. I'm going to go x. Now it turns out that your answers from here are what goes in these spots. So it would be x minus 8 and then x plus 3. The problem with this is if you distribute it, you wouldn't get what you're supposed to get. Like, for instance, just start to times this. What's x times x? It's already wrong. It's supposed to be 2x squared. So that's where the slide rule comes in. The slide rule means I take these numbers and I divide them by whatever my coefficient is. It's not just always divide by 2. You divide by whatever your coefficient is. Then from there, we reduce and slide. So like, for instance, what's 8 over 2? So that just is done. That's not going to slide. Does 3 over 2 reduce? No. So this slides out front, and we would get 2x plus 3.
Did you say, though, that we could leave that as 3 over 2 because of what we're under?
No, I didn't. I said that if you wanted to, I think Gilbert was the one who loved to not do. If you're going to ZPP this, then yeah, you can just stop there.
Okay.
But if it doesn't equal 0, then you have to factor it. And when you factor properly, you got to slide that 2 back up. Now, just to show you that this works, watch what happens. What's x times 2x? 2x squared. Then I would have a 3x, and I would take away 8x, which would leave me with negative 5x. And then negative 4 times 3 is negative 12. So we're going to stop there for today. And when we come back tomorrow, we're going to jump into slide rule with end of the fourth, which won't be that big of a deal because think about it. If this was x to the fourth, what would be here and what would be here? X to the 2 and x to the 2. So we'll talk about that tomorrow. So people who are remote, you don't have to stay on any longer. People who are here, you're stuck until the bell.
Mr. Rhodes gave out like worksheets today,
I know.
which was crazy.
That does sound so crazy.
He was like,